Hello everyone, I'm Michail and I'm going to present dynamic neural portraits, a method for controllable video portrait synthesis. This work is done in collaboration with Dr. Stylianos, Ploumpis and Professor Stefanos Zafeiriou. We define a video portrait as a sequence of frames captured by a monocular static camera that depicts the head and upper torso of a single individual. Deep generative models have shown very promising results in synthesizing photorealistic videos of human faces, by explicitly controlling the head pose, facial expression, and eye gaze of the synthetic footage. Early attempts to full head reenactment were mainly focused on GAN-based image-to-image or video-to-video translation networks, which conditioned frame synthesis on 3D face renderings or PNCC representations. More recently, NeRF-like systems have been proposed for controllable video portrait rendering. Our method draws inspiration from implicit neural representations, as we leverage neural networks to parameterize video portraits. For our baseline approach, we follow practices from conditionally independent pixel synthesis and utilize an MLP network that predicts the color of each pixel independently. To be more specific, let PI be the head pose and EI be the facial expression parameters, recovered by a face tracking system from frame I of a training video. Then, we estimate each pixel's RGB value in frame I with an MLP network C, using the pixel coordinates and the tracked pose and expression vectors as inputs. We can achieve superior results in terms of visual quality and execution speed by combining the MLP with a CNN-based decoder. Following the paradigm of recent 3D-aware GANs, instead of predicting RGB color values, we propose an MLP that maps its input to a visual feature vector. We achieve more accurate eye movements by adding eye gaze angles GI as additional inputs to the MLP. Furthermore, introducing per frame learnable latent variables VI as inputs improves the temporal stability of our results. We adopt positional encoding for the low-dimensional inputs of the MLP. We evaluate the MLP at each pixel location and accumulate the resulting feature vectors in a feature map. Then we apply the decoding network, which receives the feature map and performs upsampling to synthesize the final output. Our system can be either driven by expression blendshapes obtained from 3D fitting or by audio features coming from acoustic signals. We optimize the MLP and CNN jointly on the task of frame reconstruction. We optimize a separate network for each video portrait. Finally, we further improve our method's performance by adding an extra output layer to the MLP that predicts color values and minimizes the distance of the predicted color from the ground truth. We compare the generative performance of our system with recent state-of-the-art methods on the task of reconstruction, also known as self-reenactment, audio-driven reconstruction, and reenactment. Our numerical evaluation indicates that our architecture outperforms the previous methods across all metrics related to successful reenactment and frame reconstruction. Here, we present a visual example of our reconstructed video. Our approach achieves superior results in terms of image quality and reconstruction fidelity. We further showcase our model's performance on the task of cross-identity reenactment. This involves fully transferring the head pose, facial expression, and eye gaze from a driving actor to a target person, while preserving the identity of the latter. Our method transfers facial motions more accurately than its competitors. Here, we demonstrate the contribution of the decoding network in the visual quality of frames, as well as the importance of the learnable latent vectors to the temporal stability of the video. Thank you for watching our video. You can find more in our project's webpage